Hello, my name is Chris Mendes, and I will be presenting the first part of our project, which focuses on the cinematic modeling of a scissor jack mechanism. The objective of this work is to develop a mathematical model capable of describing the motion of the jack and relating the motor input to the vertical displacement of the lifting platform. The system consists on a sensor drive driven by a electric motor through a computer trained on a power screen mechanism. Using this configuration, we can analyze how the motor motion is transmitted through the mechanisms and ultimately convert into the lifting motion required to raise a vehicle. Before analyzing the velocities and accelerations, it is necessary to define the geometry of the mechanism and understand how the motion is transmitted from the motor to the jack. The next one is compound gear train kinematics. The first study analysis was studying the compound gear train. Instead of using a single large reduction gear, the transmission was divided into two stages. This configuration allowed us to achieve a high reduction rate while keeping the mechanism compact. And the first stage consists of a 12-tooth pinion driving a 48-tooth gear. The second stage uses the same configuration, and by multiplying both reduction stage, we obtain a total gear ratio of 16 to 1. This means that motor speed of 1200 RPM is reduced to only 75 RPM at the power script. Although the rotational speed decreases, the available torque increases significantly, which is exactly what we need for lifting load saving. Using the script pitch, we then convert rotational motion into linear motions and obtain a constant net velocity of 0.375 centimeters per second because the motor operates at constant speed and the input acceleration is assumed to be zero, which simplifies the subsequent kinematics analysis. Then the next slide is geometry constraints and angular relationships. So after defining the input motion, we establish the geometry model of the mechanism and a Cartesian coordinate system is placed at the center of the lower base. And the positions of the main joints are described using coordinate geometry. Since the lines are considered rigid bodies, their length remain constant throughout the motion, and this condition generates two log closure equations that describe the geometry constraints of the mechanism. Using trigonometry relationships, we express the coordinates of the moving joint B as functions of the leading angles. For these relationships, we derive an expression for total leading height on the jack, and this equation is important because it directly connects the mechanism geometry with the vertical displacement experienced by the vehicle during lifetime. And the next slide is the velocity analysis. When the position equations are established with difference then with respect to the time to obtain the velocity relationship, and for the lower link, the horizontal motion imposed by the script produce an angular velocity of the mechanism, and this allows us to determine both the angular velocity of the lower arm and the vertical velocity of the point B. Next, we apply relative velocity analysis to the upper limb, and by combining the velocity contributions of the translational rotation, we derive the final expression for the vertical velocity of the lighted platform. And one important observation is that the lifting velocity is not constant. Even though the script moves at the constant speed, the platform velocity changes continually because it depends on the instantaneous geometry of the mechanism. This behavior is characteristic of scissor-type lifting systems and highlights the non-linear nature of the mechanisms.
So the next step was the acceleration analysis. Since the screw velocity is constant, its acceleration is zero. However, the angular velocities of the links still vary due to the geometric effects. By differentiating the velocity equations and applying the chain rule, we obtain expression for the angular accelerations of both links. Then, using rigid body acceleration relations, we determine the acceleration components of point V. Then the horizontal acceleration is zero, which is consistent with the constant speed input motion, and the vertical acceleration depends on the angular velocity and angular position of the mechanism. Finally, numerical values were assigned to all geometric and operating parameters. The motor speed was fixed at 1200 rpm, producing a cruise speed of 75 rpm and a linear input velocity of negative 0.375 centimeters per second. The lower link angle was selected as an independent variable and varied from 15 to 65 degrees using 1 degree increments. Substituting all previous relationships led to the final governing equation for the vertical acceleration of the platform. This equation was implemented in Excel to evaluate the position, velocity, and acceleration of the scissor jack throughout its complete lifting trajectory. These results provide a complete cinematic description of the mechanism and establish the basis for future dynamic force and power analysis.
In this slide, we present the Excel-generated graphic corresponding to the kinematic analysis of the lower link AB. This link connects the fixed base to the central joint of the jack, and its rotational motion is what drives the entire lifting mechanism. On the left graph, we can observe the angular velocity of the link as a function of the angle theta3. The curve starts at its highest point at lowest angle and decreases consistently as the angle increases. This tells us that the link rotates much faster at the beginning of the lifting process and gradually slows down as the jack extends. On the right graph, the angular acceleration shows a very similar behavior, with peak values at lowest angle that drops rapidly toward zero as theta3 increases. This confirms that the most of the dynamic effort in this link occurs during the initial stage of the operation. This slide shows the kinematic result from the upper link BC, which connects the central joint to the load platform. On the left, the angular velocity curve is very similar in shape to that of the lower link, starting high at low angles and decreasing steadily as theta3 increases. This similarity is expected given the geometry coupling between both links through the central joint. On the right, the angular acceleration also peaks at low angles and decays rapidly as the angle increases. One interesting observation is that the acceleration of the upper link drops slightly faster than that of the lower link, which reflects the geometry asymmetry between the two links' length and how it distributes the dynamic behavior differently across both elements. In this slide, we analyze the motion of the load platform, which is the output of the entire mechanism. On the left, the vertical velocity graph shows how fast the platform rises as a function of theta3. At low angles, the platform moves at its maximum speed, and this velocity decreases significantly as the jack extends. This means the car is lifted quickly at the beginning and slowed down as it fast reaches higher position. On the right, the vertical acceleration follows the same trend, starting high at low angles and dropping sharply towards zero, meaning that at higher angles the platform moves at nearly constant velocity. Finally, this slide shows how the lift height h increases with angle theta3. The curve is non-linear, which is typical for scissor jack mechanisms. The jack starts close to the ground at low angles and reaches its full height at the maximum angle. The height increases at the beginning and gradually slows down at higher angles. This graph is the geometry foundation that supports all the kinematic results shown in the previous slides.
These graphs show the angular speed and angular acceleration of links BC and DE. The angular speed increases gradually as the mechanism moves. However, the angular acceleration presents oscillations. which may be caused by the screw mechanism. Since the screw transforms rotational motion into linear displacement, small variations in the thread movement and in the geometry of the scissors jack can generate fluctuations in acceleration. For this reason, the acceleration graph is not completely smooth. These graphs represent the angular speed and angular acceleration of links AB and EF. The angular speed decreases slightly at the beginning and then increases as the scissors jack opens. This occurs because the geometry of the mechanism changes during the lifting motion. The angular acceleration shows oscillations, which may be caused by the central screw mechanism. Since it transforms rotational motion into linear displacement and can generate small variations in the motion of the links. In this case, we had to assume a constant linear speed in link CD due to the position mates and constraints used in the SolidWorks assembly. We first tried to apply a rotational motor to the worm screw, but the mechanism did not move correctly. For that reason, we used a linear motor on link CD, which allowed the complete assembly to move. Therefore, the linear speed graph is almost constant because it represents the input condition used in the simulation. Thank you.